So I think let's just begin since we are on time and there's enough people already. So we are super happy to have Gautam Rao from Harvard, who's going to come and who's going to tell us something about learning from others. So Gautam, whenever you want, you can go ahead, and people will essentially just interrupt you. They'll unmute themselves and ask questions. So you have about an hour, 15 minutes.
Okay, perfect. Thank you for having me. It's a pleasure to give a talk at ISI. By the way, those of you who can, if you're able to turn on your cameras, that would be nice. It's nice to see faces and not just a screen full of names. All right, so this is joint work with two terrific PhD students, John Conlin and Matthew Ridley. And an RA who worked for us in the field and is now off to grad school herself, Malvika Mani, as well as my collaborator, Frank Schilbach, who's a faculty member at MIT. By the way, the title of the paper has changed, and we're in the process of doing kind of a major revision of the paper. And the title of the version I sent you was called Learning in the Household. And we're now kind of thinking the paper in some sense is about something broader, are thinking about figuring out how to reframe the paper. And so, comments on that are also greatly appreciated. So we now call the paper more broadly Learning from Others. So there's kind of two motivations for this work. The first is an interest in studying information frictions within the household. So just to state a kind of obvious fact, there's plenty of opportunities for learning or social learning within the venue of the household, right? Different household members often have access to independent pieces of information, perhaps through different social networks, through their different, life experiences, labor market experiences. And economic models of the household assume implicitly full pooling of information within the household. And this is a very reasonable assumption, we might think. But we do have recent work kind of documenting the fact that sometimes when incentives are different or preferences are different, spouses might strategically hide information from each other. So to be a bit heteronormative, so husband and wife, they want something different. They have a different desired, say, ideal fertility level. They might hide information from each other about, access to contraception, for example. But we think in many, many, many situations, spouses have broadly common objectives, to invest money wisely, to send their child to a good school, to consult a competent doctor. And here, making good decisions requires spouses to pool information. But there's actually surprisingly little evidence on how well spouses learn from each other. And if there are issues or barriers or frictions, what are the factors underlying those frictions? So that's one motivation for the project. Another is that there's two broad ways.
Just one question. So you pointed out that there may be strategic reasons to hide. In the case that there are common objectives, what would be the source of the friction as such?
I'm going to tell you in just a few slides. Okay. All right. So the second kind of, perhaps in some sense, broader motivation for the project is that very crudely, there's two, very broad ways people learn about things. They learn through their own experiences, and they learn through some kind of social learning, through communication with others, right? Through observation of others. And this paper is going to show that people respond less to information from others compared to information they uncover themselves. So what I experience, what I uncover, what I discover shifts my beliefs more than essentially exactly the same information when it's coming from someone else. And we're going to show that that seems to hold up in our very sort of controlled, contrived lab experiment, even when that information is perfectly observed or communicated. Okay, so to kind of, let me tell you in a moment, answer Avarup's question, but to make progress on these questions, what we're going to report to you today are results from 4 different experiments we did, in 3 of them in Chennai in India, 1 in a large online sample in the US and UK. Some of these experiments, one of these experiments was with married couples in Chennai, and the rest were just, like a standard lab experiment, teaming together pairs of strangers, either in Chennai or in the West. And the research questions we're asking are, do people respond similarly to information uncovered by themselves and by others? Does this vary by gender and by relatedness? And is inefficient learning, and here a hint of what we were thinking about, Abhirup, is inefficient learning due to a lack of communication or due to an incorrect use of communicated information? Okay, so the study was motivated by field observations on a different project where I got the chance to observe many married couples in Chennai making decisions together about, you know, what to purchase and things like this. In fact, there we were much more interested in differences in preferences. But one thing I noticed is, you know, the frequent existence of barriers to communication, even in a married couple. That is, the wife might feel hesitant to say something, to share something that she knows, or something about her preferences with her husband unless he asks her. So these were the kinds of observations that, you know, made me think there could be frictions in communication within the household. But we also thought all along, well, even if information is communicated, there could be issues of overconfidence, you know, beliefs about gendered things, or even something more fundamental than that. That's kind of where we were coming from. Okay, so to make progress, to answer these questions, we're going to show you results from, you know, many different variants of an experiment, which is really going to feel to you like a, you know, basic statistics problem that you would have seen in grad school. So participants will be faced with a very simple incentivized task, which is to guess the share of red balls in an urn. So the balls are red or white, and you need to guess the color composition of the balls. In order to have some information, you know, we first set your prior, and then you're going to draw some balls with replacement from the urn. Okay, so you just have to do a very simple stats problem. Of course, as all of us know, if you've ever tried, it's very difficult to do Bayes rule. So this is not a project about how close are people to being able to do Bayes rule. That's not what we're asking. But we're going to vary the way people get access to this information. So in a control condition, which we're going to call the individual round, people are going to draw all signals on their own. So you're going to be playing the game all by yourself. You're going to draw all the balls by yourself. You're going to make some guess about the share of red balls in the urn. And then we have kind of the crucial treatment conditions in what we'll call the discussion round. You're going to get some draws yourself, but some of the draws you can access only through a face-to-face, unstructured discussion with your teammate, right? And in some of the experiments, the teammate is going to be your spouse. In some of the experiments, the teammate is going to be some, you know, stranger that you're paired with. Okay, but very simple. All you need to discuss with them is, hey, what did you draw? How many balls did you draw? What was the composition? And you can get the same information. So we're kind of interested, are people actually able to do this? Is a married couple, you know, who've been together for years, have all these incentives to cooperate in many ways, are they able to share this information with each other?
Awesome. Are these signals to the agent, are these signals correlated, or does he know that the signals are independent?
No, these are IID. I mean, these are draws with replacement. It's going to be a literal physical urn with physical balls. I'll tell you more.
But that's the experiment. I'm talking about what is the belief structure of people. I mean, once you're out of this, you know, I mean, it's difficult to explain always IID stuff to people, right? And you're basically looking at behavioral responses. So do they actually think that they can? So because I'm kind of wondering how people, I mean, that's what you're going to show, how kind of trade off their own signals vis-a-vis whatever they can get from others. But in some sense, the belief that people have on what it contains information, this may be different from the experimenters kind of saying that these are IID and stuff like that, right?
Yeah, so why don't I show you a bit more of the design, and then I think that'll address that question. You know, in some sense, you're saying, well, I have some information already. What's the value of more information, right? So maybe it's not so valuable to get more signals when your spouse or partner tells you what they drew, given that you already know something. Right. The design is going to exactly deal with that issue. So you'll see in a minute. Okay. So as I said, in one of these treatments, you know, you learn this information. You have the potential to learn this information through a discussion with someone. That's the discussion treatment. In the draw sharing treatment, this is going to seem a little bit crazy, but wait till you see the results. We are going to ensure. So in the discussion treatment, you know, what idea we had in mind is, well, actually, there could be shockingly communication frictions, even in this very simple setup, which is not some very loaded setting where I want 3 kids and you want 2 kids and we hide information from each other. No, it's about the balls you drew from an urn. I'm going to show you how we align financial incentives. We thought, well, even there might be some communication frictions. People may not actually share information with each other. We said, well, what if we have a treatment that eliminates communication frictions? And that's what the draw sharing treatment is. In addition to your having a chance to discuss with your partner, the experimenters are going to directly inform you of your teammates' signals. Okay, so this would say, well, we shut down the communication friction, if any, and now we're going to see, well, once you know your partner's information, how much does it affect your beliefs compared to information you've uncovered yourself? And finally, in some later experiments, we've done some things that are even more extreme. We've allowed you to directly observe your partner, your teammate, drawing signals. So for example, drawing balls from the urn, you're going to be in the same room at the same desk while they're doing it. Okay. All right.
Gautam, can I ask a question?
Yes.
So I was wondering, so benchmarking the communication between spouses against the stranger communication, whether it's sort of, I was wondering whether it's too stark. The middle point being communication among peers or somebody in the social network.
Yeah, I mean, I think it's a very, very interesting question. And I think it's something we're very much thinking about as a future agenda. I mean, I guess partly it depends on whether we would find differences, right, which we didn't know ex ante. It's kind of nice to do experiments with very different, with big differences that you see is something different, and then you realize there's something to explore in between. And that's exactly, I think, the world we end up in. And actually, we are now very seriously thinking about kind of pushing much more to learn about what we are thinking of calling like relational learning, like learning from people you're familiar with, looking at, and given the hierarchy in Indian society, you might think learning between elders and youngers within a family, between siblings, between cousins, between friends, between neighbors, because we do think it seems to matter, at least in a particular way. So yeah, I think that's a great question.
And among the spouses, do you know about their history in terms of did they know each other before getting married and so on?
That's a very good question. So we did not ask. I think we might have asked about a love marriage versus an arranged marriage, and I think it was a very small share love marriage, but we didn't ask exactly what you just said. And we know things about the length of the marriage, relative education, relative labor market participation. We also have some questions about things like household decision making, who tends to, who has more decision rights within the household, sort of asked separately of each partner. So, in the paper, I'm not going to show you this today, but in the paper, we have some heterogeneity by these things, which I do think is interesting. And it does predict some of the results, but, not a lot. It explains a bit of the heterogeneity, but not a lot. All right. So in terms of kind of the related literature, I think we're trying to build on and contribute to literature on beliefs and learning in the household. As I mentioned, there's all this recent work on strategic hiding or mistrust of information within the household. There's other papers that, not necessarily the focus of the paper, but happen to show evidence for or against intra-household spillovers of information intervention. So some information provided to one member of the household, to what extent does it spill over to another? There's a broad experimental economics literature and of course the psychology literature on the role of gender in sharing and listening to information or ideas. And then there's this, literature on social learning more generally, which in the field has tended to sort of document things like barriers to information seeking and diffusion within a social network. And in the lab, I think closest to us, has sort of shown that people underreact to information implied by others' actions. So these are these information cascade type experiments testing models of herding. And one thing you tend to find there, I mean, frankly, for me, it's a very complicated, even though it's a simple experiment, it's very complicated, right? You see a stream of people making decisions ahead of you. You have to try to infer their signals from their actions. You have to form beliefs about, well, what did the person before me, how did they make sense of the actions of the person before them? And what did they think that person did in terms of the actions of the person before them? So it's kind of complicated. And in that setup, as you may know, people find that, you don't get kind of, it doesn't seem to be completely rational. People underreact to the information that they should rationally be able to extract from others' actions. Okay. So let me dive into what we've done, and I'm going to start by showing you the sample of the married couples. So these are couples recruited from where we run a lab in Chennai and have been for for a decade, a relatively kind of low income neighborhood, and the sample is of course all married, on average married for about 12 years. Men in the sample are on average about 36 years old, women are a bit younger, about 8 years of education, actually very similar between men and women, right? This is Chennai. Literacy is very high. Being able to multiply, two numbers together, that's much less likely that people can do it right, and there's a little bit of a gender difference. But I would say broadly similar education and literacy across husbands and wives. And these are people who've been together a long time. So, right, you might think that's, I don't know, based on your personal experiences, if you think a longer length of marriage would make you better or worse able to communicate, but there's some heterogeneity here in the sample. Okay, so a bit more details about the task. It's going to be in the Chennai experiments, like in the Indian experiment, it's a real, actual, real world physical experiment with an actual physical urn in it, like a matka, which actually has balls in it, which are red or white. And people are explained very clearly, there's going to be 20 balls in here. And that a computer has randomly decided the number of balls that are red and white in every round, and there's very good comprehension on this. We do a lot of work explaining these things, making sure people understand what's going on. And the computer has randomly decided something between 4 and 16 of the balls are red and the rest are white. Okay, so we're setting a common prior for everyone in the experiment. So if you don't get any signals and you just had to guess, you sort of guess somewhere in between. I'll tell you about the incentive scheme in a moment. In each round, you're going to get 2 sets of draws with replacement, and the number of draws you get is going to be randomized, 1, 5, or 9. You'll see why it's 2 sets of draws in a bit. That's actually going to deal with actually Abhirup's comment about how do people think about additional information? Is it more or less useful? Okay, and so you get a draw with replacement. Once you draw it yourself, you see the ball, it goes back in, and then, the experimenter kind of shakes the urn. So that's how you're getting kind of these IID draws. What are incentives like? So the way we do this is we want to create aligned incentives. That is, we want both, partners to have incentives to share their information with their teammate, as well as to acquire information from their teammate. So in this design, participants are going to make a bunch of guesses. And what we're going to do is we're randomly going to pick one guess out of all the guesses that the individuals in the team make in the course of their participation. And we're randomly going to pick that to be paid out. And you're going to be paid based on how close your guess is to the truth, right? So suppose the urn has 11 red balls and you guess 11, you're exactly correct. You're going to get 210 rupees, okay? And then we have a simple linear scale. This is for simplicity, for explaining to people kind of what the incentives are like. And the further away you are from the truth, the less you make. Now, for those of you who are experimental economists or theorists who've thought about belief elicitation, you'll note that this is not a proper scoring rule, right? We're not doing, for example, some quadratic scoring rule, which means that what we're, in principle, what is being elicited here, this is not an incentive mechanism to, in principle, get you to say the mean of the expectation of your belief distribution. Now, you may also know there's even more recent work, which makes a lot of sense, saying no participant understands these things anyway. So mostly people are just trying to do their best. But what we can do here, is we can calculate what a risk-neutral Bayesian would guess. So given what you've seen, given the draws you've seen, if you were a computer doing Bayes rule and you were risk-neutral, we can say what you should guess. We're not imposing that. That's not an assumption. It's not required. It's just a useful benchmark we can provide to you. Okay, to give you a sense that what people are doing is, broadly not, broadly sensible. Okay, critically, right, the incentives are now aligned across spouses, because what's going to happen is I'm going to randomly pick one of your draws. It could be yours, one of your guesses. It could be your guess or your spouse's guess. I'm going to pay you based on the accuracy of that guess, and that payment will be split 50-50 across the partners. Literally, you'll get cash in an envelope, you'll get cash in an envelope, and you guys will be on your way. Now, of course, especially when we're doing this experiment with spouses and not with strangers, I think we should all worry about what happens as soon as the couple leaves the office, right? Like they could just redistribute the money. Maybe the husband takes the money, maybe the wife gets the money. But, at least in principle, they both have some incentives to share with each other. Okay, it's not a competitive environment in that sense. Okay. Now, why did we do this task? Like why this balls in an
So can I ask you a question?
Yes.
Why did you do it as a random payment to one of them? Why not just pay both of them?
I'm sorry, I wasn't clear. It is a random payment to both. Sorry, of course. So it's a randomly selected guess made by one person, will be paid out based on its accuracy, and that payment will be divided equally between both people. Right. So supposing my wife and I are playing randomly, I made a guess. I went through this experiment. I made a guess about the composition. My wife made made another guess, both in private. Sorry, I'm not showing you this part yet. We're going to randomly pick one of those two guesses. Say my guess gets picked, and we'll both be paid equally based on how accurate my guess was. So the idea is that when I'm making guesses, when I'm deciding whether to share,
I mean, what I meant is, I suppose you could have paid them based on the average that you would pay if you paid both guesses.
Oh, I see. Well, no. So we don't want to do that, because that creates things like incentives for hedging. So if you want to pick one guess randomly to pay, because this then makes, in some sense, the guesses, you can't have a strategy like, oh, I'm not sure, it could be really this or it could be that. So I'll guess this and you'll guess that. So then you would have an incentive that we've seen exactly the same information. We're risk averse. There's some uncertainty about the true answer, even if I'm totally doing Bayes' rule right. You might then have some incentives to hedge across your guesses. Plus, as I'm going to show you, each team plays many different rounds of this experiment. That is, they play the experiment repeatedly in different conditions. And if you're paying people for multiple guesses, again, you're going to start creating, dependencies between these guesses. So it's kind of a very standard kind of trick or approach.
I don't understand that. If your experiments are independent of each other, right? So how will you create dependencies?
Precisely. So think of it like a portfolio kind of thing. So supposing you have some uncertainty about what's the right strategy, how should I interpret information? This is one way to do it. That's one way to do it. And now you have multiple different stocks, right? You're going to not select them independently. You might try to, basically you can get hedging kind of incentives. So yeah.
Yeah, but each round is independent, right? You said they played this several times, you said.
Yes, you'll play it several times. Why don't I show you more of the design? I'm very confident that actually, if we were paying people for multiple rounds, I mean, in practice, okay, so first let me say what I think in practice would happen. I think
so no, I'm not saying multiple rounds. I was just saying within the round.
Yes. Okay, even within a round, I think you'd end up with this issue if you were paying for both. I don't think in practice it would be a major issue. So let me say this. These are the kinds of things that experimental economists are often trying to be very careful about, which I think don't actually matter in practice. So I suspect it wouldn't matter. But,
I get the point that you made, that if people were risk averse, then there's an incentive to that if you use the average, then you get there's some incentive to spread, right?
Yes.
So that's your point, which you don't want.
Yes, that's exactly right. Yeah, that's the answer.
Okay.
Yeah. Okay. All right. So why do we kind of broadly take this approach? So some key features of the design are that we can create a common prior. So supposing we were thinking of a much more field application, like here's some information about a good school to send your kid to. There's many schools in your neighborhood. I give you information about these things. First, it's kind of very hard to elicit prior super well, and we can't kind of set a common prior. And second, there would be in most real world things, some strategic incentives might creep into play, right? So for example, a father might really care about the daughter going to walking a lower distance to school. The mother may care about the quality of the school. There'd be sort of all these incentives for potentially for strategically hiding information that may show up. So here we're able to artificially align incentives for the reason I just said, right? That you're both getting paid equally for either of your guesses. So there should be, in principle, at least no financial kind of reasons to behave strategically here. We can precisely vary each person's information. That is, how much information does each person have? And we do this by randomizing the number of draws. So for example, perhaps I got one draw, and you got 5 draws. Right? So you're better informed than me. And as I said, we can calculate kind of a useful benchmark, which is a risk-neutral Bayesian guesses. And in terms of kind of broader design considerations for the task, we wanted something that's simple enough to be well understood by a sample with relatively low education. So these are not college students and so on. Yet sufficient complexity to allow some wiggle room, right? These data have to be interpreted. When you've seen a certain, you got 7 blue, 3 red, there's something to think about and some possibility of you're not completely agreeing. And there's, most importantly, perhaps there's a very simple, clear prediction we can test. And that prediction is of information pooling, right? Which is that you treat your own and your spouse's information equally, right? The goal of this exercise is not to test the various biases that people might have that cause them to depart from Bayesian updating, right? Informing their guess. The goal is to say, does it matter whether 2 red balls were drawn by you or by your spouse, right? And if you're pooling information, if there's no frictions, if you're putting equal weight on information, it should not matter. So that's kind of what this round, this design helps us with. So bear with me, this is a bit complicated. I'm going to spend now quite a bit of time getting into the details of the experimental design, and then we're going to exploit that for the rest of the talk. So this is for the experiment with the married couples. Each couple plays 5 rounds, in a randomized order. We did some overly clever, randomization, which I don't want to get into. But I'll tell you about the content of these rounds in a bit. So the individual round is sort of this control condition I've mentioned where you play by yourself. There's a couple of discussion rounds. These are the ones where you need to have a face-to-face discussion with your partner to learn their information, perhaps discuss your guess, perhaps they help you do the math. You have the draw sharing round. This is the one where, in addition to getting to discuss with your partner, the experimenter just tells you exactly what your partner drew. I'm not going to talk about the guess sharing round. No, this is one where the experimenter tells you what your partner's guess was, not what information your partner uncovered. I won't talk about it today, given the results obviated. Okay, so here's what happens within each round. Okay, on the left is the individual round. And here's how it starts. It starts by the husband getting some, random number, H number of draws. This could be 1, 5, or 9, and people know that this is randomized. And the wife getting W draws. These are both from the same urn, in the same room, so they kind of have to walk in and out of the room. So when you're playing this individually, your partner is not in the round, right? Is not in the room when you're doing this. Okay. So you get some draws and you make a guess. And this is a guess that, just like all the other guesses you're going to see on this slide, has some chance that this could be the guess that's chosen to be paid out and the money split equally between husband and wife. It turns out that the other 2 rounds are going to start in exactly the same way. So that's exactly what happens in the other 2 rounds as well in the beginning. Where they start to get different is in this second set of information. So what happens here? Well, in the individual round, the husband just gets some more draws and then makes another private guess, right? So within the round, he gets some draws, makes a guess, gets some draws, makes a guess. Same thing for the wife. In fact, the way we designed it, by the end of this, the husband and wife actually both have an equal number of draws, H plus W, W plus H. Okay. So at this point, on average, they're equally informed. I mean, they are actually exactly equally informed. How is that going to be different than the discussion round? Well, the difference in the discussion round is instead of getting these private additional draws by yourself,
So are they paid for each round? Or are they paid? Is this that's not clear to me.
No, they're one guess across all the rounds is randomly picked to be paid out. So every guess that you make has incentives for guessing, in the sense there's some chance that this is the guess that will be picked to be paid out.
So they only paid once for the whole experiment.
Exactly. I mean, they're also paid a show-up fee and stuff, but only one guess out of all of these guesses that you're going to see on this slide will be randomly picked to be paid out. So your incentives are in some sense sort of similar in all guesses. Any of them could be picked out. They're all real stakes. Of course, these are not big stakes decisions, right? You can make 200 rupees from a very good guess. So it's not a huge amount of money. Yeah.
And how long does the whole thing take?
So it depends. So there's also kind of a fixed show-up fee that you get. So in the end, participants, I think on average, make about 500 rupees from participating, if I remember correctly. And it takes an hour, like depends on the depends on the couple, like it can go a little faster or slower. And depends on what's happening in the lab. I think it takes like an hour.
What was your show-up fee?
I think it was about 300 rupees or so, 250, 300 rupees, something like this. Details are in the paper. I'm forgetting the exact number. Yeah. So people are making I think about 500 rupees for about an hour or two of their time. Something like that. Okay. All right. So, sorry, let me just get back to where was I? Okay. So what happens in the discussion round? So in the individual round, remember, you've gotten some information, made a guess, gotten some more information, made a guess, all by yourself. In the discussion round, instead, this second set of draws, which in the control condition you get by yourself, what happens instead here is that now you have a discussion and you have the opportunity to get this information from your partner. Okay, you may get it, you may not. You may talk about additional things. Your partner may help check your math. All of these things could happen. But in principle, I should say this is totally unstructured. People can take as much time as they want. It's face-to-face. They're also asked to make a joint guess here. I talk about that in the paper. I'm not going to focus on it in the talk in the interest of time. But the idea is that the husband can now learn his wife's W draws. The wife can learn her husband's H draws. And so in principle, if communication is happening kind of fluidly, like without frictions, by the end of this, you should be exactly as informed as you would be in the individual round, right? You each have access to H plus W draws. The difference is just, do I get all of them by myself, or do I need to uncover some of them through a discussion with my spouse? Okay, and that's going to allow us to kind of test for information pooling. The focus in this, in the analysis I'll show you today, is always going to be on these final private guesses. So, right, even in this joint discussion round, I have a discussion with my spouse, and then we are both separated again. Okay, we're both separated, we're in separate rooms, and we get to make a final private guess. Okay, and so if we compare these private guesses from the individual and the discussion rounds, we're going to be able to ask, is information uncovered yourself weighted differently than information potentially learned via a discussion with your spouse? Okay, and with information pooling, it shouldn't be. Right? If people are good at communicating,
Did we lose the speaker?
I think so. Let's see. Meeting.
Well, Zoom has been scratchy. Huh? I've been logged out a couple of times already.
Oops, it's gone. Where is this guy? He's been logged out.
guess they have power cuts now in Boston also.
Okay, he's back.
Hello, everyone. I'm sorry, I'm not. My internet went down for a moment, which is very rare. Okay, can you see the slides again?
Yeah.
Okay. Sorry about that. So, sorry, give me a moment. Okay, so I was telling you guys about this draw sharing round. So in the draw sharing round, let me back up a bit, right? It's going to be a lot like the discussion round, except that there's this stage in between where we try to eliminate communication frictions. So, in piloting, as I was mentioning, I've seen examples where, so I saw an example where a husband and wife come into this discussion together. It's kind of like a, slightly older couple. It happened, I had been there, in the previous part, so I knew that the husband had gotten 1 draw and the wife had gotten 9 draws. So she was much better informed than him. They walk into the discussion together and he doesn't even look at her. He just says, here's the decision, here's what it is, that's it, we're done. And her face kind of becomes a bit small, but she doesn't say anything. And in kind of a private debriefing with her, conversation with her later, I asked, hey, so what were you thinking, what happened? And what she said to me was, well, it would be very inappropriate. Like if he had asked me, I knew he was wrong. If he had asked me, I would have corrected him, but it would have been very inappropriate for me to just sort of come out and unsolicited, provided my information, which disagreed, with his. So those were the kinds of communication frictions that, we thought might be quite important. And so we designed this treatment to shut that down, which is basically saying, I get told by the experimenter, something like your wife got 5 draws, of which 4 were white and 1 was red. And then I actually make a private guess. So if you think of this private guess here and compare it with the private guess you made at the end in the individual round, it's going to feel like it's a very clean kind of comparison. The difference is just, did I draw these balls myself, see them with my own eyes, right? Or was I just told by the experimenter what my partner's guesses were? Okay. And then they know that they're going to, in a few minutes, get to discuss it with their spouse, verify, that the experimenter is not telling them some nonsense and so on, something like this, and then make a final private guess. Right? So we can make this a comparison of these 2 private guesses to ask, is information uncovered yourself weighted differently than information uncovered by your spouse, but perfectly shared with you? Right? And here there's been, in both of these cases, there's been no opportunity for joint deliberation. You didn't get to actually discuss with your partner and put your heads together and say, how should we process this information? What's the best guess? And there's also no communication frictions, right? But note that we can also compare the very final guess here after you've also had this discussion, compare it with the, compare across this part of the experiment. And this is sort of saying, well, you got to discuss, you got to, check your logic, so on and so forth. The only difference is that we're sure on the right here, there's no communication friction, and on the left, there might be. Okay. All right. So that's the design. I'm going to now tell you how we're going to present the results. And actually, I'm only going to, in the paper, you're going to find, some attempt at a kind of a non-parametric way of showing you the results. So trying to get as close to showing you the raw data while being, able to process it. We're going to plot the average guess you made as a function of the signals you saw, okay? And how do we do that? We don't want to show every possible combination of 10 draws because that would be overwhelming. So we're going to do something very simple, which note is not what the Bayesian should do or like focus on, which is the net red draws. Okay, so if I happen to get 5 draws, 4 of which were red, 1 was white, that's 4 minus 1, 3 net red draws. Okay, so we'll sort of on the x-axis have that, on the y-axis say what did people guess, and do that separately by kind of the source of information. Was it your own draws or your spouse's draws? Then I'll show you a reduced form, which is just imposing a linear slope on that graph. And then I'm gonna, we also have in the paper, which actually gets us more power and is more interpretable if you're interested in thinking about, Bayesian updating, or sort of quasi-Bayesian updating model, where weights on signals are allowed to differ by the source of information. And we're going to test, are you putting equal weight on information, coming from your partner or uncovered by your partner versus uncovered yourself? Importantly, we're always going to compare responsiveness, like how much your guess is sensitive to the information from the second set of draws. Okay, we're never going to be comparing, let me go back to the full design. We're never going to be asking how much weight did you put on these draws compared to these draws, right? This is precisely, or at least, one version of, there's a broader, set of concerns related to what Abhirup said. There could be things like recency effects. There could be things like base rate neglect. There's these different things people could do, which might cause them to overweight the first set of things they saw, right? So Abhirup maybe potentially had that in mind. Like, I got some information myself, I made up my mind. Then I hear from my spouse, I just don't think more information is necessary. I already know the truth, right? That would be if I looked at this discussion round and I said, how much weight did the husband put on the draws he got versus the draws he subsequently learned, right? There could be some order effects, broadly speaking. And we have theories in behavioral economics of ways people would get this wrong. We're never going to make that comparison. I mean, you can in the paper if you want, but we're always going to be comparing how much weight are put on the second set of information, depending on whether you got it yourself, or you got it via discussion, or you got it via draw sharing. Does that make sense? Okay. All right. So let me show you first.
Yeah, can you go back? I don't think I understood. So what do you mean by the I didn't understand what you meant by the second set of information. So at the end of this, they know the results from W plus H draws. Is that what you mean?
Yes, yes, that's right. They know the results from W plus H draws. We're going to look at how much, we're going to look at these final private guesses and say how responsive or sensitive, how much are the final private guesses affected by what they happen to see here, right? Obviously, it's going to depend also on what they saw up there. That's going to be kind of the same across all the treatments. It's always drawn
in the left, you don't know the information from the other draws, right? In the middle, you do.
From your partner draws, you don't. Exactly.
So on the left, you know only either W draws or H draws.
No, that's not correct. So on the left, you.
Oh, sorry, because you get to draw the second time. So you know your own W plus H draws.
Exactly.
Okay, right. So it's always the same number that's being compared.
Exactly.
Okay, got it. Thanks. Yeah, go ahead.
Okay. So before showing you kind of treatment effects or differences and so on across the different rounds, let me start by just establishing some facts that we were thinking that one role here, we tried to choose a task that wasn't very gendered, that is not very gender stereotyped. And in that we kind of succeeded, but we still thought there could be big gender differences in things like overconfidence and so on. So let me tell you a bit about that. So when you're playing by yourself in that individual round, right, the one where there's no need to communicate, you don't communicate with anyone, you just do this by yourself, men and women actually perform very similarly. And so these are the kinds of non-parametric graphs I'm going to be showing you later. So let me explain. On the left side of the figure on the left is for husbands playing by themselves. On the x-axis is what they saw in their second set of draws. Okay. So how many, if I drew 5 balls and all of them were red, right, I'm going to be in this bin. 0 is if I, maybe, you can't be exactly 0 because it's an odd number of draws, but 1 means I drew 1 and that was red. Okay, -1 means I drew 1 and that was white. So that's how we're kind of binning these data and then just showing you means. And on the y-axis is what you guessed, that is the number of red balls you guessed. So note some things. First, this is upward sloping as it should be. The more red balls you saw relative to white balls, the more you're going to guess that there are red balls in the urn, right? Great. And then we have kind of this benchmark. So the pink dashed line is what a risk neutral Bayesian, if a computer were seeing these data and were risk neutral facing the incentive structure that we created, that's what the computer would guess on average, right? Or not on average exactly, but we're averaging across anyway, all these things you could see. Okay, so this is what a computer would guess. And what you see is that on average, people are not very far from that. Of course, there's heterogeneity and some guesses are going to depart more than others from what a computer would guess. Note that as I said, this is not a paper about can people do Bayes' rule right. There are many reasons why actually you might be flattered. Risk aversion is one of them. There are also some other more complicated reasons to do with the exact structure of our task and so on in some corner cases. There are things that would cause you very rationally to be flatter than the Bayesian, the risk neutral Bayesian, okay? But the important thing I want you to note is that husbands and wives both do approximately equally well and both do on average fairly close to a risk neutral Bayesian. Go ahead.
What's the dark line?
Oh, sorry. So the dark line here, I apologize, are husbands' actual guesses at the end, right? So remember, we're always going to be looking at these final private guesses. So the dark line, right? So the y-axis is what did husbands actually guess? So what we're plotting is, for husbands who saw one more red draw than white draw in the second set of information, on average, they guess something like 12. That's what that's showing you.
Then what are the dots?
Oh, the dots are the data. Like this is like a
non-parametric fit. Yeah, just a non-parametric fit, right? That line.
Yeah, just a non-parametric plot of the data. The dots are the actual data, and then we have some fit here.
Piecewise linear fit.
I think so. I don't remember what this is.
Looks like it.
Yeah.
All right, go ahead.
Yeah. Okay. Okay. So this is what husbands are doing. Then on the right is what wives are doing. Gray, the solid gray is the actual guesses of the wives. And the things I want you to notice is that both spouses are basically equally good, and they're fairly close to risk neutral Bayesian on average. I'm not showing you this here, but men and women, interestingly, also have similar levels of confidence. So we do quantitative elicitations of how, for your individual private guesses, like how much do you think they're going to earn on average, where, you get 210 if it's a perfect guess and so on and so forth. So we kind of get these beliefs. We actually have some incentives for accurate guesses too. And we find that men and women are both overconfident. Actually, they think they're going to earn more than they actually will, that their guesses are more accurate, but they're similarly overconfident, which is kind of interesting. Okay. All right. So those are the preliminaries out of the way. I'm now gonna get to results. Okay, I'm going to start by showing you the couples experiment, with these non-parametric graphs I've shown you. And what this graph is telling you is that husbands' guesses are less sensitive to their wife's signals than to their own. So the gray line is a line you've seen before. That's the husband's guesses when they're playing all by themselves. Right? And remember, this slope is capturing how sensitive are their guesses to the information they uncovered. Okay. And the blue line is the information that their spouse, their wife, drew, which the husbands then had a chance to sort of learn about via a face-to-face discussion. And you're going to see that the blue line is flatter than the gray line. Right? This means that husbands' final private guesses, so what husbands guess after the discussion when they're all by themselves again, that guess is more sensitive to the information they uncovered themselves compared to the information they may or may not have learned through a discussion with their spouse. Okay, so this is, of course, here I'm not doing a statistical test. You're not seeing standard errors. I'm going to show you that in the regression, right? But this is
what happened to these guys is the spousal thing for more than 5 net red. That's a big drop, right? I mean, was it? Yeah, because it kind of goes up all the way to the top, right, near the individual, and then suddenly there's a huge drop in number of guesses for red balls.
Yeah, I don't want to overinterpret a particular point. The size of these markers of these balls is proportional to the amount of data. Like this is a very extreme draw.
I see.
Like my partner got 9 draws, and so there's not a lot of data there. So that's part of it. But in some sense, part of this might also be like if my partner gets some extreme information, maybe I'm actually putting less weight on it in some way, or there could be some of that.
Right.
Okay. All right. So this is saying that, well, in the discussion, something is perhaps going wrong. Okay. So now I'm going to show you what happens when we eliminate the communication friction, right? The experimenter just tells you, remember, like, hey, your spouse, your wife got 5 draws, 4 of them were red, or whatever it was. It turns out that doesn't help at all. Okay. So knowing exactly what your spouse drew, husbands are still putting, much less weight on that information in terms of how much it affects their final private guess. Okay, so communication frictions aren't really what's driving what we're seeing on the left. Even knowing your partner's draws, now you may worry, do they believe the experimenter, and future experiments I'm going to show you are going to deal with some of those concerns. Do they think the experimenter is lying to me? We have no incentives to. It never came up in debriefing, but who knows? But this is not, by the way, and this result is going to persist if after we gave you this information and you made this guess, you went and discussed with your spouse, you could verify the information from them. Again, you may have made a private guess. You're still not going to get equal slopes. It's going to look just like the graph on the left. Okay. Now these are husbands' guesses. Now, what about wives? But wives' guesses look very different. It turns out that in this context, wives are actually putting exactly equal weight on information they drew themselves and information that their husbands drew, which they could learn through a discussion or which they were perfectly informed of by the experimenter. Okay, so here we're showing evidence of within the household, this real difference in learning from each other, where husbands seem to be neglecting to a substantial extent information originating from their wife, even if it's perfectly communicated to them, but wives are not doing the same, right? In a setting where men and women are exactly equally good at this task on average, are equally confident and so on, there's no notion of having better skill, there's no notion of, there's none of that, and yet you find this. I'm going to show you now the reduced form, the sort of regression coefficients. And what I'm going to do there is very simple. Each of these lines that I'm showing you here with these spiky plots, I'm just going to impose linearity and estimate the slope. Okay, and I'm going to show you the slopes. If you're interested, I can show you the regressions that this is coming from, but I think it's just going to mostly waste time. So, I'm happy to go back to it if anyone would like to know. But really, all I'm doing is showing you the slopes of each of those different lines I've already shown you. Okay, and now with confidence intervals and p-values and things like that. So very consistent with what I just showed you. You might have been wondering about statistical power and significance in those graphs. So these are the regression versions. So the gray bar is the slope of husbands on, on their own information. How much does their final private guess relate to the net red draws in the second set of draws that they got themselves, all by themselves, right? So what you're going to find is, right, there's a certain amount of weight. The more red balls I drew, the more I guess there are red balls. That's what the gray bar is. And the blue bars are the information that their wife drew, okay, which they had a chance to learn about through a discussion, which was exactly, they were informed by the experimenter. And this is, they were informed by the experimenter, and then they had a discussion with their spouse, and at the end of all of that, okay? And what you're finding consistent with the figures I showed you is that husbands are, their final beliefs or guesses are much less responsive to information and statistically significantly less responsive to, the balls that were drawn from the urn by their wives. And you don't see that at all for wives, okay? And this is in a design that's dealing, this is not about order effects, what I saw first or, last or something like this. And remember, this is not just about a failure to communicate. Even if communication frictions are eliminated, we find this.
So what you have here on the vertical axis is a slope coefficient.
Yes,
So
exactly.
You're basically assuming those things are straight lines and then checking the difference in slopes.
Exactly.
Got it.
And doing it by running a very simple OLS regression and so on. Yeah.
Okay.
Okay. Now, note, it's kind of just follows from what I showed you. It's that husbands earn less when the second piece of information was collected by their wives. Okay, so now on the y-axis here is your earnings, or rather something that's actually even better here is like the expected earnings from your guests. Like what would if you had seen this, what, and if you'd seen this, what would you expect your earnings to be, kind of taking care of the noise, like the sampling error. And gray are husband's guesses in the individual round when they're playing by themselves. And these 3 points on the x-axis are whether in the second set of draws you randomly got 1 draw, 5 draws, or 9 draws. As you imagine, if you got more information, you're going to make better guesses and therefore earn more, right? That's the gray. But that's not true, right? If the information, these 1, 5, or 9 draws were not drawn by you, but were drawn instead by your wife. And Abhirup, this is exactly the fact that this 9 thing is going down so much. This is exactly the thing you identified on the non-parametric graph, right? Where it's really costly to ignore your wife's information when your wife has a lot of information, right? So that's kind of where, men particularly do poorly. Now, remember, in our setup, when I make a bad guess, it equally affects my payoffs and my wife's payoffs because, the payoff is split equally. Okay. And this is true kind of in this draw sharing round as well.
Gautam, am I right in saying that that looks like a less than 20 rupees difference?
Yeah, these are not huge, right? These are not huge stakes. Yeah, absolutely. Yeah, that's right. Okay.
So why are you, one thing I don't get here is, why are you plotting the number of second rows? Because the information on which the guess is being made is, I thought, an even number, right?
The information on which the guess is being made is, I don't think it needs to be even, but it is, it is the first draws and the second draws. But remember, we don't, the experimental variation, like everyone gets the first set of draws themselves. It's the second set of draws that we either get ourselves or learn through discussion or informed by the experimenter. And so that's what we want to focus on. I mean, we could include here also something about the first set of draws, but this is the part that's actually varied, right? So remember, the goal is not to say how good are your guesses compared to all the information we're having. We're just saying how well do you do based on whether the second set of information comes from these different sources. The first set of information is always by yourself.
So can you infer from the second draw from the number of second draws what the number of first draws was?
No, no, you can't. No, that's not how the randomization is done. No.
I thought you said that you always get H plus W.
Yeah, the only round in which you can do that is the individual round. That's not true in the rest. And in the individual round, it doesn't, what the first set of draws was when you get the second, but that's not going to be true, I think, in general across that. Yeah, that's a good point. That's a good question.
So you're not really conditioning then on the same information in this graph. If that's, I'm not sure I understand what's going on here. Is the information comparable here?
Yes, the information
in the sense that, yeah, I mean, if you got 9, if your second draw was 9.
Actually, let me check something. Sorry, give me a sec. Sorry, it's been a while since we ran this one. Actually, I take it back. Sorry, I take it back. You're right. In principle, you could infer if you figured out this part of the setup, which I think people were not told about. Sorry, I take it back. It is, you're right, that it is H plus W by the end each time. There's going to be variation.
Yeah, that's what I thought you said at the beginning. It's always H plus W.
Yeah, so it's definitely true in the individual. I think it's true in the rest too. Now, exactly what is H and what is W? Is it 1? Is it 5? Is it 9? That's going to be randomized. So it's not that H plus W always adds up, for example, to be 10. It could be that it was 1 and 1. It could be 1 and 4, 1 and 5. So that's going to be randomized by round. So it's not that it's not the case that every single time by the end I should have 10 draws. So that's going to vary, but it's going to be balanced on average through the randomization. but it is true that it's going to be.
But it's going to be
you will
balanced
have-
on average, right? But it's not going to be balanced on each treatment. So then I'm wondering whether your comparisons are valid or not.
Yeah, it is. So comparisons. So two things. So it's going to be balanced on average. We're showing these. What I'm showing you here is on average.
No, but when you show us 1, 5, and 9 second rows,
yeah.
my question is conditional on. Yeah, here.
Yeah.
Maybe it's true that that the information that people were conditioned. Let's look at the 9, right? That's where they're clearly different, right? The others, not so much in the left-hand panel. So is the information that they're conditioning on the same at the end of these second rows? And I think what you said is that's true on average, but it is in fact not necessarily true with the particular sample you observed.
No. I think it's actually going to be true for each case, but maybe we'll see if it's possible I'm misunderstanding you. So
I get 9.
I see what you're saying. Yeah. Okay. I got it. Yes. I understand what you're saying. Yeah.
Because
So
these 1, 5, 9 are
the
different strata, right? I mean, the thing is that what you're saying is across 1, 5, and 9 in the whole experiment, the average number of draws for different treatments will be the same.
Yeah.
But conditional on the fact that there is a draw in the second round, would the averages be the same? I mean.
Yes. The averages will still be the same condition on that, but it's true that, see, this is averaging across all the couples in the sample, right? But it is going to be the case that for a particular couple, if you're comparing within that couple individual versus discussion round, I think it's not necessarily that you got the exact same number in the first round, but averaging across, it's going to be true. I should note
So
that
then it's,
sorry,
so my point is that you need to, what I'm saying is there's a balancing condition, which is true in expectation, that it needs to be checked in the sample. It may not hold.
Oh, it holds. No, we've checked that, and you're going to, I think, probably
conditional on the 9, really. That's the one where you have, well, on the right-hand panel with the draw sharing, it's both 5 and 9.
Yeah, I think our randomization.
You need to show us those balancing conditions. Otherwise, just the fact that these are different isn't sufficient to tell us that that's because they didn't make use of the information. Because we don't know from this how much information they got in the first round.
Yeah, so I'm definitely not going to show you.
You get my point?
Like that now. No, I take your point. I mean, I think things should be fine. We can certainly double check. Yeah. So yeah. I mean, I think we've checked for balance. I think the randomization.
No, you need to check for balance between the conditional on your second draw being 5 and being 9.
Yeah, no, I
then you need,
yeah. I take your point. I'm not going to show you that today, but that's something we can check. I think we have checked. I just don't have a table for you right now. Okay. All right. I have less than 15 minutes, so I'm going to move along. So the results I've shown you so far are, might kind of have sparked the question in your mind, sort of a pretty obvious question, which is that, well, you've shown these differences between husbands and wives. Are these sort of gender differences specific in some way to married couples, or is this just turns out to be some more broad gender difference? Perhaps men and women, are just differentially open to information coming from others, right? So, we also thought of this question, and therefore, what we did was basically repeat more or less that same experiment again, and now, recruited a very similar sample in a similar way, and then people were randomly matched with the people who showed up, on a given day. So you're playing with strangers. We make sure people don't actually know each other. And you could be randomly matched to play with a man, to play with a woman. Most of the sample is, is mixed gender pairs. So a man playing with a woman. Okay. Demographics are pretty similar age, similar education, and so on and so forth. And in fact, many of these people are married, but now the sample also includes a bunch of unmarried people, particularly unmarried men. Okay. So, all right. So what do we find here? We find that men actually behave quite similarly with strangers as with their wives. Okay, so this is the same reduced form sort of figures I've shown you before. And what you're going to see is that, men, in terms of the weight they're putting on their own information compared to their teammates' information, the teammate is now a stranger. Here I'm pooling whether the stranger is a man or a woman. And they're putting kind of, that the teammate is a man or a woman, and they're putting less weight on information from their teammates. In the paper, you'll find the breakup by, most of the sample is men playing with women. It's going to look very similar. Men playing with men turns out to also look basically the same. It's a little bit less precise. There's a smaller sample for that. Okay. So in a way, men are treating their wives like strangers in terms of kind of how much weight they're kind of giving to their information. Okay. But now we find something that's a bit different than before. Here we actually find that women are also putting lower weight on strangers' information. The point estimates are not quite as stark, although they're not significantly different than they are for men. But women are putting, putting less weight on information coming from strange men compared to their own information. Okay. And, this is also broadly true for women playing with other women. Again, that's even less precise. So now this sort of, this pattern of results kind of changes a bit our interpretation of what we've seen so far. My guess is that until now you were thinking, and we were thinking, wow, men are being very, very strange. Men are failing to attend to this very sort of, simple information coming from their partner, from their wives. But now we find that men and women both tend to do this when they're learning from a stranger. Okay, so perhaps there's kind of a general tendency to do this, and perhaps the exception to this norm is actually women playing with their husbands. That is, women might have some additional force that's causing them to kind of equally weight information coming from their husbands. But everyone in general has a tendency to underweight information coming from others. To dig deeper on this result, we're going to then do a couple of additional experiments. I should say controlling for covariates, whether you're married or not, kind of none of this really seems to explain the difference. So, I've shown you that women playing with strangers are playing differently than women playing with their husbands. You might think this is because of a difference in demographics, or maybe married women are different than unmarried women, age is different, so on and so forth. So you can kind of control for all those things. And that doesn't really seem to explain the difference between these two samples. Virup, you were going to ask something?
No, I was just trying to ask. I guess you're going to look at mechanisms, but I'm just thinking whether this has got to do with some sort. Obviously, it means that in a marriage setup, men essentially discount anything that they get from their wives, or at least not paying much attention to that. And I was wondering whether the heterogeneity among the women, which would, in a more descriptive sense, kind of give their relative, I would not say bargaining power, but relative say in decisions, would condition some of these results. So I was just wondering whether, but maybe that's what you look at right now.
Yeah, that's a great question. I'm not sure I have all of that here. We don't find very robust patterns of this. You'll find it in the appendix of the paper. These not amazing measures, but just self-reported, some measures of, who's the main household decision maker for various kinds of affairs. Does that predict things? Not so much. Depends on exactly how you look at it. It does seem to be the case that if a person in the household says, I am more the decision maker, then they put a little bit less weight on their partner. But I don't want to oversell those results. I don't think, the results are not super precise, I would say. And of course, when you're playing with strangers, who knows exactly what's, there is no notion of that. Yes. Okay. I don't want to spend too much time talking about these confounds, which we try to think about quite a bit. This is not driven by order effects. It's not driven, should not be explained by confusion or errors in probabilistic reasoning. We don't need to be Bayesian. Comprehension scores are excellent. We try to be careful to kind of keep secrecy of the guesses to avoid any possibility of punishment of any spouse by another for, not listening to them or something like that. These can't be explained by differences in ability or confidence or risk aversion. Those should not be relevant. And anyway, there aren't differences on most of those things. Okay, so just in the few minutes I have left, let me tell you about a couple of additional experiments we did. This was one which was again in Chennai.
Just one small question. So did you, since you said that different couples took different amount of time in the discussions, did you measure the amount of time that you, and was that an important kind of play? It's a bit like in being instinctive. I'm not thinking about this kind of Sean Frederick kind of idea, but now as a couple decision making, that you just do it instinctively versus you take some time to think about it.
Yeah, it's a good question. Yeah, we did measure the time. It's usually about like 1 to 2 minutes is usually what the couple minutes of discussion is what they're taking. It's in the paper. I don't remember off the top of my head kind of if there's heterogeneity by that. We also did some measurements. We also randomized, is someone in the room when they're discussing or not? That actually had no effect. So in some sense, I think because of the striking result we find in the draw sharing round, we're being perfectly told about your partner's information, you still don't update that much. In a way, in the paper, that's obviated a lot of the importance, that's downweighted the importance of like exactly what's happening in the discussion, because it seems like, well, even if you shut that down, there's these issues. So, okay, we're going to do this third experiment. We did this third experiment again with strangers in Chennai, which is just looking at this striking draw sharing round and doing versions of it. Okay. And we find that basically none of the following really seem to clearly eliminate the underweighting of others' information. Perhaps the most striking one is what I call kind of this in-person round. So the participant is in the same booth, basically sitting at the same table while their teammate is drawing their signals. So you randomize the order, who goes first, and then the other person goes, and then you are separated and make your private guesses. Even there, you put more weight on the information that you drew. Okay. There's other things we did like, oh, well, maybe the issue is because you've made your first guess after getting information by yourself. Kind of if you've made some guess about the world, you've gone on record in some way, perhaps that makes you less open to more information coming from others, from your partner. Otherwise, you might be open. So what if we didn't have people make a first guess? What if we reverse the order of information? And this one actually maybe does matter a little bit, but which is that, what if you learn your partner's information before you've even had any draws yourself? Right? Imagine your partner tells you something and you have no way of thinking that I know anything about this more than them. Right? Maybe that will eliminate the lack of weight put on your partner's information. We also randomized increasing the stakes by 50%. None of these things really mattered very much. As an example, this is the in-person round. This is the one where you're right there sitting by your teammate when they draw balls. You're still actually putting less weight on their information than the balls you drew yourself. Okay. And finally, we kind of replicate this experiment and try to do a little bit more on the underlying psychological mechanisms by running a large, I think, 4,000 person experiment. Online version of this thing with a sample in the US and UK. We pre-registered, all of these experiments. And in this one also, we pre-registered that we don't think the effect sizes are going to be the same. First, it's a very different, sample or population, but also the experimental paradigm is very different. And particularly, first, online experiments tend to find smaller effect sizes than in-person experiments, a thing in experimental economics. But secondly, that in a way, my sense was that the fact that, you're putting your hand into an urn, you're drawing a ball, it's a very visceral thing that kind of feels closer to learning through some experience of your own, the way some of the things we learn are in fact like this, through experience, through doing something physical in the world and having some visceral sensations, whereas just seeing some urn on a computer screen may just not generate the same thing, okay? So anyway, we did this experiment in the US and UK to kind of understand the different cultural context, higher numeracy sample, and more importantly, to understand some things like what would be the most extreme treatment we could think. The balls are being drawn by a computer, and all we randomize is a label which says, these are your draws, these are your partner's draws. Okay, will that generate an effect? Or does the vividness of the information matter? That is, when you are drawing balls from an urn, it's a very vivid experience. Whereas when the experimenter tells you your spouse got 5 draws, 4 were red, 1 was white, it's not vivid in the same way. right? And that's true about a lot of communication. When we learn from experience, things could be very vivid. When someone just tells us in summary form, hey, here's my advice, that could not be very vivid. I mean, unless they're a fantastic storyteller and so on, right? Or it could be, and I think this is what we're going to show some evidence for, that what really matters is taking some action, putting some effort. You have to do something to learn when you're learning by yourself. And that kind of causes that information to feel like, you have some sense of ownership, you pay more attention to it. So we kind of basically try to do the same draw sharing treatment you've seen before. You're going to click a button to draw balls one by one from an urn, and you're just going to be told a summary of your teammates' draws, just like in that experiment. You're going to have kind of this watch draws condition where you click a button to draw balls one by one, and you observe your partner's draws appearing. You obviously don't have to generate those draws. You see them appearing on the screen. And then the most sort of extreme version, you have to just sit back, relax. You can see your draws appearing. It says, these are your draws. And then you see more draws appearing. It says, these are your partner's draws. So it's just a pure labeling effect. What we're going to find is, let me see. Okay, sorry, this never works. I try to have a video in the PDF, but it never works. So what we find is that people underweight their teammates' information in the draw sharing round, just like before, right? Smaller effect sizes. They underweight their teammates' draws still in the round where they have to click to generate their information and their friend's information just appears. But they don't really do it when they just have to sit back and it's a pure labeling effort, okay? So it seems like you kind of need to take some action to have the information feel like yours and therefore weight more than others do. Okay, I'm out of time, so I gotta stop. Yeah, happy to talk a bit more. We've kind of shown evidence of a general propensity to underweight others' information and shown that one exception to that we found is that wives place equal weight on their husband's information. So, we think there could be many implications of these results more broadly for social learning and for learning inside the household. But of course, this is a very sort of controlled, contrived experiment, and there's lots more work to be done. Thanks so much for your attention and your comments.
Okay, yep.
So is there time for questions?
Yeah, maybe we can take, I don't know, let's do maybe 5 minutes.
Okay. So yeah, so I was wondering, I mean, so the non-parametric graphs are really informative. So and what is important is that, if I noticed correctly, the smaller amount of draws, so -1 +1, there is not a lot of gap. So I think it's in the extremes, or I mean, relatively extremes, is where the flattening is taking place. And given what you showed subsequently, which is this 5 or 9 draws is where there's a gap appearing. So I was wondering if you can say a little bit more. I mean, I guess probably run into power issues, but if you can say a little bit more about when you have an opportunity to learn a lot, i.e. when you have opportunity to draw several times, extreme outcomes are going to be very informative, but that's where I think you are discounting it. So if you discount extreme outcomes from others a lot, and the only way you can get extreme outcomes is when there are large possibilities of draws, right? And I was wondering if it's possible to check for that in sort of the US UK example where you have larger sample size.
Yeah, I love the question. One thing that I haven't shown you is the structural model, which also relates to Som's point from before about the balance. So when you do the structural model, you actually account for the exact information each person has seen for each guess, like exactly what was in the first draws, what was in the second draws, the exact structure is there because you can just model all of that. Right? So for every guess, we know exactly what they saw. And so, by the way, even if there were any imbalances there, that would take care of that. And, you're going to get qualitatively exactly the same kind of conclusion. I think we could do what you're saying, Sabyasachi, which we haven't done, is by estimating the structural model separately for when there's more draws versus fewer draws. So in a way, it's a little bit hard to kind of say what you're saying based on this reduced form stuff, because after all, what should enter a Bayesian's posterior is not in any case the net number of draws. The number matters, right? If you got 100 draws and it was, 0, 1, like versus you got, one draw and it was net 1, it's very different, which is all mixed up here. Right. So you want the structural model to do that. And we've not done the structural model saying, let's separately put in large number of draws versus small number of draws, because the structural model will account for the fact that you should update your beliefs differently based on large and small. And that's kind of hidden here. So it's a little hard to conclude what you concluded, that in fact, it's driven in that sense by the extreme ones. And you kind of see some, like, of course, if it's just one draw, you would expect you can't see much because they're just it's not a strong test. And exactly, maybe we could see that in the big sample, but you see it for like 2 draws, 3 draws, small number of net draws here too. But yeah, I love the suggestion. Thank you.
All right. So I think we should just wrap up now. So thanks to our speaker, thanks to everyone who showed up, and thanks for your comments.